Nonstandard analysis is a branch of mathematical analysis that deals with the concept of infinitesimals and infinitely large numbers. It was introduced in the 1960s by the mathematician Abraham Robinson. Before delving into nonstandard analysis, it's crucial to have a solid understanding of real numbers and limits. Real numbers include all the numbers that can be found on the number line. This includes both rational numbers, like 7, -3, 5/2, and irrational numbers, like the square root of 2, pi, e. Real numbers can be added, subtracted, multiplied, and divided except for division by 0. And they can be compared to see which is larger or smaller. The concept of a limit is a fundamental building block in calculus and analysis. Informally, the limit of a function at a certain point is the value that the function approaches as its argument input approaches that point. For example, consider the function f(x) equals to x squared. As x approaches 2, f(x) approaches 4, so we say that the limit of f(x) as x approaches 2 is 4. This is written as limit x tends to 2 of f(x) equals 4. Limits can also be used to describe the behavior of functions at infinity. For example, the limit of 1 over x as x approaches infinity is 0, because as x gets larger and larger, 1 over x gets closer and closer to 0. Limits are used to define many important concepts in calculus, including derivatives, rates of change, and integrals, areas under curves. They are also used to define continuity of function as continuous at a point if the limit of the function at that point is equal to the value of the function at that point. Understanding real numbers and limits is crucial for studying more advanced topics in analysis, including nonstandard analysis. These concepts provide the foundation for understanding how functions behave and how they can be analyzed and manipulated. Now, let's move on to the infinitesimals. The concept of infinitesimals dates back to the early days of calculus. As developed by Newton and Leibniz, an infinitesimal is a quantity so small that it is closer to 0 than any positive real number. Yet it is not 0 itself. It's a way of talking about quantities that are infinitely small. In the original formulations of calculus, infinitesimals were used to define derivatives, the rate of change of a function, and integrals, the area under a curve. For example, the derivative of a function at a point was defined as the ratio of an infinitesimally small change in the function's value to an infinitesimally small change in the function's argument. However, these early uses of infinitesimals were not rigorously defined, and this led to paradoxes and logical difficulties. In the 19th century, mathematicians reformulated calculus using the concept of limits, which provided a more rigorous foundation. In the 20th century, however, the concept of infinitesimals was revived and given a rigorous foundation through the development of nonstandard analysis. In this framework, infinitesimals are treated as a type of number, and they can be manipulated using the usual rules of arithmetic. The introduction of infinitesimals provides a new way of looking at the concepts of calculus and analysis. Instead of talking about limits, we can talk about quantities that are infinitely small or infinitely large. This can lead to simpler and more intuitive explanations of many mathematical concepts. Okay, now, let's proceed to hyperreal numbers. The hyperreal numbers are an extension of the real numbers, which includes not only all the real numbers but also infinitesimal and infinitely large numbers. This system was developed as part of nonstandard analysis by Abraham Robinson in the 1960s. The set of hyperreal numbers is denoted as R, which is a superset of the real numbers R. Every real number is also a hyperreal number, but there are hyperreal numbers that are not real. In particular, for every real number x, there are hyperreal numbers that are infinitesimally close to x. That is, their difference from x is an infinitesimal. These numbers are of the form x plus epsilon, where epsilon is an infinitesimal. Similarly, there are hyperreal numbers that are infinitely large. That is larger than any real number. These numbers are often denoted by the symbol omega. The hyperreal numbers obey the same basic arithmetic rules. As the real numbers, you can add, subtract, multiply, and divide them except by 0, and they form an ordered field. Meaning that you can compare any two hyperreal numbers and say which is larger. The introduction of hyperreal numbers allows us to deal with infinitesimals and infinite quantities in a rigorous way, and it provides a foundation for the study of non-standard analysis. Now, it's time to talk about the transfer principle. The transfer principle is a key concept in non-standard analysis that allows us to extend properties from the real numbers to the hyperreal numbers. Here's a more detailed explanation. The transfer principle is based on a branch of logic called first-order logic. In first-order logic, statements are made about all, or some, elements of a set, but not about all subsets, or some subsets. For example, the statement, for all real numbers x plus 0 equals x, is a first-order statement. But the statement, the set of all subsets of the real numbers is uncountable, is not. The transfer principle says that any first-order statement that is true about the real numbers is also true about the hyperreal numbers. This includes basic properties like, for all real numbers, x and y, x plus y equals y plus x, the commutative property of addition, as well as more complex properties like the intermediate value theorem or the mean value theorem from calculus. However, the transfer principle does not apply to statements that are not first order. For example, the statement, the set of all subsets of the real numbers is uncountable, is true for the real numbers, but not for the hyperreal numbers. In the hyperreal numbers, there are infinitely many numbers between any two real numbers. So there are more subsets than there are real numbers. The transfer principle also does not apply to statements that involve a fixed real number. For example, the statement, for all real numbers x less than 1, is not true in the hyperreal numbers, because there are hyperreal numbers that are greater than 1. Despite these limitations, the transfer principle is a powerful tool in non-standard analysis. It allows us to use our knowledge and intuition about the real numbers to understand and manipulate the more exotic hyperreal numbers. It also provides a rigorous foundation for the use of infinitesimals and infinite numbers in mathematical analysis. Non-standard analysis can be used to simplify and provide new insights into many areas of mathematics. For example, it can be used to give simpler definitions of the derivative and the integral in calculus. It also has applications in other areas such as probability theory, differential equations, and even physics. But non-standard analysis has been the subject of some controversy in the mathematical community. Some mathematicians have embraced it as a valuable tool and a source of new insights, while others have criticized it as unnecessary and overly complex. Despite this controversy, non-standard analysis has been the subject of much research and has proven to be a valuable tool in many areas of mathematics. In conclusion, non-standard analysis is a fascinating and rich area of mathematics that provides a different perspective on many concepts in analysis and calculus. It allows us to work with infinitesimals and infinitely large numbers in a rigorous way, and it has many interesting and powerful applications.